Thank you very much. Thank you very much. I hope it's okay. Yeah, so thank you. Thank you for letting me present on this topic. I'm going to present some of the work that we have done on HS2 on our contract C1 within Jacobs, part of the Align joint venture. So we're going to present a couple of case studies and interesting assets that we have designed over the course of the last few years on HS2, especially the Colne Valley South Embankment and the some of the shaft design lesson learned and examples. So we will go over what is the contract C1 and what are the assets that form part of that contract as the main the works that were done on HS2. The main topic of the Colne Valley South Embankment, I will present it briefly, and some of the site settings, location, and geology. Also part of the investigation and site investigation and testing that were done around the area, and general approaches and examples of the geology, ground model, and ground conditions. Then we will dive into the main issue that drove all the design on this asset, which was relic shear surfaces and relic slip surfaces, and the some of the slopes that the embankment was built on, and how the design evolved, and what were the implications, and how we came up with a robust engineering solution. Then I will jump over some of the other case studies that we present today. Is the design that was undertaken for the Chiltern tunnel ventilation shafts. So we will go over ground condition, ground challenges, and how was finally designed, and some examples from the construction and the performance that we are currently recording. So as an overview of the C1 works, Align is a joint venture that comprises these construction companies. And we as in Jacobs, we are integrated in a joint venture with Geohazards or Rendell as part of the Align D joint venture that is mainly responsible for the design of the assets that the joint venture is building for HS2. So as a kind of a big overview of the geology of the site or the whole contract, the C1 is entirely, or let's say 90%, within the chalk, the white chalk group. So it's comprising different geological units of the chalk around the Chilterns and the Colne Valley, and the tunnel itself crosses the entire white chalk units. So here is an overview of the C1 contract. So we have on the right of the page where we're coming from, the Colne Valley Viaduct, which is a big asset for this contract, and coming into a big part of earthworks, and then joining into a big long tunnel, which are the Chiltern tunnels. So in this particular case, we will focus on the Colne Valley South Embankment, which is on the southern end of the contract C1, and we'll present some of the examples that we have obtained from the 5 shafts that we have designed. As you can see here, the shafts vary in length and position, but they are mostly they have been positioned in a lower elevation point, so that was prone to discover faulting and other different ground risks. So we will go over some in more detail later on. So we're gonna just focus now on the Colne Valley South Embankment and what were the problems and geohazards that we encounter, especially all the periglacial geohazards and relic shear surfaces that we have encountered. So a bit of an overview of these main risks. So the periglacial slip surfaces are occur during solifluction processes that occur after the glaciation. So they have been encountered and recorded throughout many of the localized geological units. But in this case, we were very much focusing on the glacial hazard that were going to occur in the head deposits and the underlying Redding formation or the Lambeth of the Lambeth group. So we were kind of trying to figure out where these geohazards or these periglacial geohazards were present throughout these embankment, and how we have demonstrated their presence and what we did for come up with a robust solution. So as an overview of the embankment, this embankment is a 200-meter long embankment over to be built over a gentle slope. So it's in a transition with the previous contract. So that was another challenge to come up with a robust transition from a cut and cover tunnel that is well, I think it was a bored tunnel on the south end of the contract C1. So coming from Halby Road, we will we needed to design an embankment that is going to be founded on weaker or lower strength material. So that I'm going to present in a moment. So as an overview of the site and the testing that we obtained from different ground investigation phases. We were at the beginning limited by protester activities and access to the site. So at scheme design, the ground model or the ground was not probably well understood. So it relied on published literature and limited resources to understand ground conditions. So preliminary GI was not probably enough to understand the whole picture. And what we did was undertake different phases of ground investigation, including comprehensive laboratory testing and geophysics, including MassW and in a couple of phases in the year 2020. So as an overview of the site, you can see in different colors, different assets of this embankment, the different access roads and attenuation ponds, and also I didn't mention, but in green you can see a big platform for different services and adjacent services for the main route, and in dark blue or purplish color the main embankment for HS2. You can see dotted some of the ground investigation positions that we had to come up with a ground model, and I'm going to present in a moment. So as a summary, the ground conditions comprise different superficial deposits, including alluvium at the bottom of the valley that is continuing over the Colne Valley, and a head that will be covering a blanket layer over the whole slope of the embankment. And as a solid geology, we'll have London clay on top of the hill overlaying Howich Formation the Redding formation, the lower mottled clay in this case, followed by the Upton formation, which is a glauconitic thin layer of sand, probably more competent than the overlaid lower mottled clay, followed by the different white chalk units. In this case, was the Seaford chalk. We subdivided the chalk in different geotechnical subformations, mainly structureless, then weathered and more competent chalk. So here is an overview of the different geological units that we were having in this point. So you can see the slope, even though this picture shows a vertical exaggerated image, you could see the embankment being built on a slope. So with the risk of the periglacial polished surfaces, we were facing a challenge of designing a slope stabilized embankment. This is just from the top geological units, the superficial, how we will divided the superficials, and how they the solid geology would have cropped if we were removing the superficial deposits. So as you can see, the main embankment is to be found in the lower mottled clay. So that was our main geological unit and our main interest in this case for different ground consideration, soil properties, and different ground parameters. So this will be the different subunits of the chalk that we would have if we would remove everything else. As an overview of the long section and cross section, and I will show this is how we design or we derive a geological model. So you can see the head deposits kind of covering a blanket and increasing their thickness towards the end of the slope. So with that in mind, coming up with a slope stability parameters was key for this design. This is another overview of the ground modeling cross section. This summarizes some of the geophysics that we undertook. So even though it didn't cover the entire length of the embankment, we had good overview, good results that we had for different geological units. So we were able to derive ground parameters for dynamic response of the ground as well. So not only fine-tune the geological model, but also obtaining valuable design parameters for the definite solution. Okay, so jumping on to the main issue of the main challenge for these asset Reddick shear surfaces. What we first undertook is an understanding of the terrain model. So spotting solifluction features and ground movements by understanding how the terrain model was obtained. So we were able to already identify presence and proofs that the solifluction was occurring around the area. You can see there in marked with a star, a clear or an evident ancient solifluction feature that will we would infer that the solifluction or periglacial surfaces or periglacial solifluction will have occur around the area. With that in mind, we back analyzed the current slopes, and we were obtaining only a 5-degree and stable slope of 5 degrees. So that in mind, we needed to come back to the scheme design parameters, and we were studying how that would impact on the current proposal. With ground investigation, especially trial pits, with an engineer on site, this solid fluxion and these relic landslips were identified in this trial pit. So you can see there polished slip surfaces being picked up by different trial pits. So we definitely could not rule out the presence of relic shear surfaces. So with that in mind, we come up with different parameters. We plotted all the different laboratory testing, and we came up with a different residual shear strength properties that was summarized in a 11 degrees. So that made a significant change to the current proposal. So plotting it against published literature, especially the engineering geology of the Lambeth group, that didn't count with most or many data on this red formation or the lower mottled clay. We had to derive lower values for the slope stability. So with that in mind, the final solution needed to contemplate a probably more conservative assumption that the ground or the relic shear surfaces were present. So with that in mind, we had to increase the foundation treatment, extending the already proposed distribution of the driven piles that finally the embankment is built on. And the lower embankment field was to also had to be stabilized, and extensive instrumentation was proposed. Yeah. Yeah, but this is coming again. The final solution is looking something like that. So you can see a robust pile embankment over the whole length that is joining the two assets, one being the Colne Valley viaduct to the north and the Harville Tunnel to the south. So you can see here that that solution is driven by the two transitions, both south and north of the asset. So we had to limit the settlement and the differential settlement at both ends of the embankment. So that's why not only we had to mitigate the risk of potential landslips, but also adjust the settlement to both ends of the asset. I'm going to jump over now to the case study that can present on some of the shafts that Chiltern Tunnel has been considered. So it's an overview of the geological profile. Here you can see that the shafts are located in a way that that the excavation of the shaft was limited for economic purposes, but also that means most of those shafts will be proposed in dry valleys locations. So that's where more faulting is predicted, or more dissolution of the chalk is expected. So you can imagine the challenges and the different risk associated with faulting and dissolution were very much present. So as an example, shaft on St. Giles is located within a 3 dry valley. So the likelihood of coming up with or of traversing a faulted area was high. Like, I will show some of the examples that we have prepared. So this is an overview in 3D of shaft on St. Giles. So you can see there the tunnels crossing competent bedrock in blue, but as we come into the shaft position, which is, as you know, in a valley, we were very much in a faulted area. So the ground investigation confirmed lots of voids and also dissolution, localized dissolution within the area. So the shaft was in a highly probable fault. So that's why some of the consideration that later came up, those decisions were needed to be made. So the ground investigation around the shafts comprise different techniques. So mainly rotary core and wireline logging of the chalk, but it's, as you can imagine, the logging and drilling through the chalk is challenging due to the tendency to break up during drilling. Requires a careful operation to not disturb the chalk around flint area or coming or crossing void area. So televiewer and downhole geophysics was also of great value. And as you can see here in Shaft on St. Giles, voids and faulted materials was encountered, and as we have presented in the previous video. And some of the different techniques include high pressure dilatometers and pressure meters, different geophysical surveys like cross-hole seismic and 3D resistivity around some of the most challenging or most prone to dissolution and faulting areas. So crustal, as a note, crustal geophysics probably proved to be very valuable within the chalk, especially for this type of asset, because we couldn't come up with different parameters, especially K-naught, so lateral earth pressure coefficient, and I will reiterate in that later on. So pressure meter was also very valuable to derive stiffness properties. So different techniques of dilatometers were undertaken. Different parameters were derived, especially horizontal earth pressures and K-naught, and different stiffness and the stiffness at different strain levels was also been able to derive. Also mass permeability from different pumping well tests, and as I mentioned, cross-hole geophysics to derive different parameters, especially small strain stiffness. So the whole stiffness ranges are around or across different strain values, different strain ranges was possible by combining different sources. Chesham Road shaft is another example of how ground conditions derive a different solution. So in this case, significantly worse ground condition were obtained from the ground investigation. So the shaft was relocated to a more uniform, more consistent ground conditions. So that was a product or an outcome of the interpretation of the ground condition. So finally, some of the design solution that most shaft share is how the shaft share really is common internal diameter, and how the head house is being designed, even though the architecture is different for most shafts, but it was come up with this share approach. I will share they both share different the same approach for how they interact with the tunnel as they cross paths. These are some of the instrumentation and monitoring that the construction of the shaft were proposed, including surface monitoring, vibrating wire strain gauges, and vibrating wire piezometers. And some of the trigger values were determined by the design. As a key aspect for the design of this shaft was the lateral pressure coefficient. So this is an example of how the designer came up with an evolution of the K note following the different construction stages. So after the D-wall excavation, the K note would decrease, and following different construction and concreting, the K note will recover part of their value. So the end K note was different from the K note at initial stage, from following different construction stages. So this was backed up by numerical analysis and solid structure interaction, and ground or the D-wall movement were predicted accordingly. So this was integrated in different finite element modeling and different iterations. So I'm not going to jump into much detail in here. The ground shaft tunnel interaction enabled to understand the load path and the arching relaxation effects of the surrounding ground, and determine forces on the structural elements at different stages. These are allowed to optimize the design of the diaphragm wall thickness and color structure. I'm going to just present an overview of how these shafts were constructed and how the construction stages were designed. Yeah, some pictures from site, and how they different construction stages were achieved. Different piling works happened at the same time, and different structural elements were installed in different stages. As a validation of how the design outcomes were validated on site, I can just showcase a couple of examples of how the hook forces were recorded in the instrumentation in the instrument, and then how it compare against the predicted profile of the hood forces on the diaphragm wall. This allowed data for research and further development of and fine tuning of the different modeling. So thank you very much. I think I'm gonna get very close.